Linear equations are very useful in many kinds of applications in the real world. And so we're going to look at how we can take some real world problems, translate them into mathematical equations, solve those equations, and then transform them back into statements about the real world problem that we're working with. We're going to see a few different examples and a few different kinds of problems that are commonly seen in real world and in courses. And we're going to follow a general strategy again. There are a few things that we're going to want to do each time, and I'm going to keep them a little bit vague and a little bit nebulous because they really are intended to be guidelines rather than some sort of strict algorithm that we go through. So our general strategy for applying the ideas of linear equations to real-world problems is the following. It takes a few steps. So part one is we want to make sure to identify the unknown quantity. That is the quantity that the problem is asking us to find. Whenever we're working on a problem like this, we'll be wanting to figure out how many of something will work, how much of something do we need, something like this. And so we want to identify the unknown quantity and give it a label. Now that label will be a variable because it is as yet an unknown quantity. Now we want to be very precise about what our unknown quantity is, and we'll see why in a second. We'll see how in our examples. Whenever we introduce a variable, we need to make sure that the value of that variable, what it means, is very, very explicit. It's very clear that there's no confusion about something. If we say that a variable represents time, well, that's not good enough. We need to say, oh, well, time since when? Time measured relative to what? And we also need to tell what units we're using to measure it also. So we'll see a lot of examples in the problems that we're doing. So step one, identify the unknown quantity that we're looking for, give it a variable as a label. Step two, we want to express the other quantities in the problem using our variable. There are often going to be lots of quantities involved in a problem, and we can express them using the variable that we have defined in order to have a common language that we can relate the various quantities together in. Which brings us to step three. We want to find either an equation which relates two of our expressions from step two, or, which amounts to almost the same thing, we want to express the same quantity two different ways. Which is another way of saying that we're going to have an equation, because if you express the same quantity in two different ways, those two expressions you have to be equal because they're describing the same thing. Once we have an equation, we can solve the equation in step three for the variable. So that will give us a quantity for the variable, a value of the variable that is a solution to the equation that we got in part three, which hopefully is a solution to the problem that we were looking at in the first place. And then five, finally, we want to interpret our solution in the context of the problem. When someone asks a question and asks, how long will it take for such and such to occur? Your answer shouldn't be something like 7. It should have more meaning to it. You should be able to say, it will take 7 minutes for such and such to happen. Your answers to these types of questions should be sentences. They should say, it will take so long for this to happen. You need so much of this to do whatever it is that the problem is asking for. So the last step of solving a word problem or an application problem is to write down the solution in a way that is meaningful in the context of the problem. So this is the general strategy we're going to be using. As I said, there's some wiggle room in it, and now we're going to look at a few different kinds of problems, common examples of problems that we can apply the strategy here to. So let's look at a type of problem called just a number problem. And this, technically speaking, isn't really an application problem in mathematics. These types of problems just ask you to find numbers that satisfy certain conditions. So for example, we could look at the following. The sum of 3 consecutive even numbers is 60. Find the numbers. So here we're just trying to find numbers that satisfy a certain condition. So they have to be 3 consecutive even numbers. They have to add up to 60, and once we find numbers that do that, then we will have the answer to our problem. So let's think about the strategy that we had before. First, we want to identify what are the unknown quantities. And usually you can find the answer to that question in the question that's being asked in the problem or the instructions to the problem. Find this. What are these? So in this problem, the last sentence says find the numbers. So the unknown quantities in this problem are the 3 numbers that satisfy the condition in the first sentence. Now, we could give each one of the numbers a different variable, but that's not too useful for us. We want to have as few variables as possible, usually just one. Usually we can get away with just using one variable, and we want to stick with that. So if we just want to use one variable for one quantity, we need to choose one of the 3 numbers to represent using a variable. And it actually doesn't matter which one. It's often, however, a good idea to use variables to represent smaller quantities involved, smaller numbers involved, and that's just because that tends to make the problem a little easier to work with when you go through to the rest of it. So I am going to solve the problem the following way. I'm going to introduce a new variable that I want to use. And the way that we do that is we say the following. We're going to let some symbol, I'm going to use n here, let n be, now I have to be very precise, the smallest of the 3 even numbers. Okay, so we've got a variable, and so n is going to be the smallest of the 3 even numbers. And now we need to express the other quantities that we have in the problem. Well, the other 2 quantities we have are the other 2 even numbers involved. Those are the other 2 quantities that we want to express. So that means we want to know what the second even number is. But we want to express it in terms of n. Now, the difference between any 2 consecutive even numbers is 2. If I've got any even number, like 4, I get to the next even number by adding 2 to it. And I would get the next one by adding another 2 to it, and another 2. The difference between any two consecutive even numbers is 2, and therefore the second even number in this problem is n plus 2. Because n is the smallest one, and so n plus 2 will be the next one. And we can continue. The third even number is n plus 4. So 2 more than the second one. So we have 3 even numbers here that are consecutive. They come right after another. n plus 2, n plus 4. So at this point, we've expressed all the quantities in our problem in terms of our variable, representing one of the things that we want to figure out. And now we need to find some sort of equation or relation between the expressions that we have and other quantities. So here we can go back and read the problem again. Usually you'll wind up reading the problem several times. And we read in the first sentence that the sum of these 3 consecutive even numbers is 60. Well, we can write that down. So the sum of 3 consecutive even numbers is 60. We can translate that into mathematics. So the sum of 3 consecutive even numbers. We have written those even numbers as n plus 2, and n plus 4. So that's the sum of 3 consecutive even numbers. Now remember, when you are translating sentences into mathematics, the word is, or similar to be words, will usually translate into equality. So if the sum of 3 consecutive numbers is something, that is indicates that we've got an equals, and now we can take the last part, 60, and bring it down. So we've translated the sentence, the sum of 3 consecutive even numbers is 60, in the following way. We've written that as n plus 2 plus n plus 4 equals 60. And we want to figure out what n is. Now, at this point, once we've converted the statement of the problem into mathematics, we've replaced various quantities with variables and other properties, other quantities with expressions involving those variables, and translated our sentences into equations. Well, then we can just work with it from the point of view of pure mathematics, and we can say, right, what's the solution to this equation? And then we'll go back and say, well, what does that mean about the original problem? So let's see on this one. We've got the equation n plus 2 plus n plus 4 equals 60. I can simplify the left-hand side of this equation. I've got an n, and an n, so that'll all become 3n. And then I've got a 2 and a 4, so that'll be plus 6 equals 60. So 3n plus 6 equals 60. Now I can solve for n by subtracting 6 from both sides. Let's see, that'll give us 54. Then dividing by 3, and we'll get that n equals 18. Now, we can't stop here. Whenever we're working with a word problem, even a word problem that's just a number problem like this one, we have to go back and interpret this solution in terms of the original problem. So n equals 18 is the number that makes this equation true. At this point, what we want to do is go back to where we said what n was. This is why it's so important to write down very clearly what each of your variables are. So, at the very beginning, we wrote that n is the smallest of the three even numbers. All right, so that means that 18 is the smallest of the three consecutive even numbers that we like. Okay, that's one thing that we need to check. The other thing that we need to check at this point is, what is the question asking? What's the specific instruction or question that the problem contained? And this problem said, find the numbers. So this means that it would not be correct for us to respond with 18 as our answer, because the problem's asking for all three of those numbers. The problem is asking for all three of those consecutive even numbers. We have found that the smallest of them is 18, and so therefore our answer to the question is 18, 20, and 22, because those would be the three consecutive even numbers, where the smallest of them is 18, which is what we figured out from our algebra. So that's our answer to this problem. The three numbers, consecutive even numbers that add up to 60 are 18, 20, and 22. Let's look at another one. Sometimes we're looking at problems that involve geometry. And many times you will need to draw on some outside knowledge that you have about, in this case, geometry, sometimes about finance or motion, rules of motion and relationships between distances and times. We'll get to that in a moment. But geometry problems involve geometric figures and using something about those. So for instance, let's look at the following example. A person wishes to enclose their 10-foot by 15-foot rectangular pool with 80 feet of fencing, leaving a border of uniform width. How wide should the border be? Often in problems involving geometry or even other real-world scenarios, it's a good idea to sketch a little picture of what's going on in the problem. People are really good at visualizing things, at processing information visually as a general rule. And so sketching out a picture of what's going on in a problem is a good way of understanding what's going on and thinking about it. So I might start this the following way. I would start by doing a little sketch of our situation. And in our situation, we've got a pool, which I'll do in this blue color, and we're containing it with a fence. And it just has to be a little sketch. You'll notice that I haven't been super precise about this. That's okay. We just need sort of a cartoon of what's going on in the problem. And even before we do anything else, we can start here and we can start labeling what we know. So we know that the pool is 15 feet by 10 feet. Let's see, what else do we know? We know that we've got a total of 80 feet of fencing. So we've got 80 feet of fencing, and that's total around the whole green rectangle. And then let's see what else. We want to know how wide should the border be. And so this last question, how wide should the border be? Well, there's our unknown quantity. We don't know how much space there's going to be in between the pool and the fence yet. That's what we're trying to find. And so because that's what we're trying to find, that's exactly the sort of thing that we want to give a variable name to. Now in this case, I'll go ahead and use W. W for width. A lot of times using a variable that is a letter that reminds you of what it means is helpful. Now I've labeled a quantity here with my variable W, but that's not all I want to do. You still want to write down in words what each one of your variables means, so that when you go back at the end of the day, you'll be able to interpret it perfectly precisely. So, to start my solution, I want to let W equal the width of the border. And here's something very important. I have to specify what units I'm using. So W is a variable, which means it represents just a number. But there are lots of different ways that we could talk about a particular length. We could measure it in feet or inches or centimeters or any one of a million other things. So we need to specify what W is. So W is going to be the width of the border in feet. Now I've chosen feet here because we already have length measurements using feet, and you always want to be consistent with the units that you're using. If the problem is already using feet to measure length, you want to continue doing that. You want to continue using feet. In fact, if a problem gives you quantities in some units one place and a different set of units another place for the same type of quantity, you're going to want to convert all of that to one or the other. You just want to work with one type of unit for each type of quantity you're dealing with as you work through. So in this case, all of our lengths are being measured using feet, so our variable should be measured using feet as well. Okay, so we've got this situation. We need to somehow relate this quantity we don't know, the W, to the quantities that we do know, the 10 feet and 15 feet of the pool and the 80 total feet of fencing area. So what we can do is we can start thinking about what this 80 feet of fencing total measures. This 80 feet is going to measure the perimeter of the outer rectangle. So this 80 feet is the perimeter of the green rectangle. And we know that because the problem tells us that we're using 80 feet of fencing in order to construct the whole green rectangle out here. But we also know how to calculate the perimeter of a rectangle using geometry. We also know that 80 feet, sorry, not 80 feet, we also know that the perimeter of the green triangle is equal to 2 times the length of the rectangle plus 2 times the width of the rectangle. So we have two different ways of thinking about the perimeter of the rectangle, or two different ways of measuring the perimeter of the rectangle. On the one hand, the problem just tells us that the perimeter is 80 feet. On the other hand, we could get at it by understanding the length and the width of the green rectangle. So let's work on that. If we want to understand the width of the green rectangle, we can do that by sketching in a few more copies of W here. So the width of the green rectangle is going to be the total distance from the top to the bottom of the rectangle, as I've written it here. And we can see what that total length is, because that length is made up of the 10 feet of the pool plus 2 copies of the border, 2 copies of W. So this width is actually 10 plus 2W. The length of it in feet is 10 plus 2W. And similarly, we can do the length of the green rectangle. The problem tells us that the border of this pool is supposed to be uniform all the way around. So it's supposed to be the same width all the way around. And so if we look at the length of the green rectangle, that's going to be the 15-foot length of the blue rectangle, the pool inside, plus the 2W representing the width of the border on the left and the right-hand side. So the perimeter is 2 times the length of the rectangle plus 2 times the width of the rectangle, and we now have expressions for both of those. So the perimeter of the rectangle is going to be 2 times the length of the rectangle, which is 15 plus 2W, plus 2 times the width of the rectangle, which is 10 plus 2W. So now we have 2 different ways of writing down the perimeter of this rectangle. But because they're measuring the same thing, because the 80 feet from the problem and the expression with the W's are both measuring the perimeter of the rectangle, they have to be the same. They have to be the same quantity. So we have that 80 has to equal 2 times 15 plus 2W plus 2 times 10 plus 2W. Because the 2 different ways we have of writing down the perimeter have to give us the same quantity, because the perimeter only has 1 length. Well, now we have found our equation, and you'll notice that it took us a little while to do this. A lot of times in these problems, coming up with the equation takes longer than actually solving the equation itself. In fact, solving this equation isn't going to be too much of a hassle. So we have that 80 equals, if we simplify the right-hand side, we get 2 times 15 is 30, and 2 times 10 is 20. So we're actually going to get 50 out of this. And then 2 times 2W is 4W. 2 times 2W is another 4W. So we're going to get 8W. We can solve this by subtracting 50 from both sides. And we'll get 30 is equal to 8W. We can divide both sides by 8 to get that W is equal to 30 over 8, or we can simplify that and write 15 over 4. So 15 over 4 is the solution to the equation that we came up with. But we need to go back and make sure that we understand what that means in the context of the problem, and then we need to actually answer the question in the context of the question. So we have that W is 15 over 4. W, we come back up here and look, W is the width of the border in feet. So that tells us that in this problem, the border should be 15/4 feet wide. And so then we say, all right, we understand what W is now and what it means. So let's go to answer the question. The question was, how wide should the border be? Now our answer should then be what we just said. The border should be 15 over 4 feet wide. And that is how our answer should look. Now, notice that we shouldn't say for our answer something like W equals 15 fourths. That's not good enough as an answer to the original question. And one of the big reasons for that is that the original problem doesn't include a W in it. If your boss is designing this and asks you, oh, how wide should the border be? Tell me how wide the border should be. And you come back and you say, W equals 15 fourths. They might be able to guess, but they won't know for sure what you mean. You should always be very, very clear what you mean, and that's why your answer to these problems should be clear as well. The border should be 15 over 4 feet wide. Now, the other thing is to think about is whether we should leave our answer in the form 15 over 4. Now, it is true that in real life, most of the time you wouldn't leave your answer in the form 15 over 4. Usually what you do is you plug that into a calculator and get a decimal representation of it, which might or might not be an approximation. So you would plug this into your calculator and you should say, oh, well, the border should be 3.75 feet wide. And that's, to be fair, usually how you would communicate that to other people in a real world scenario. We are, for the most part in this class, going to stick with fractions as the way that we generally deal with things. We'll simplify them, but we'll leave them as they are. However, always pay close attention when you're completing your homework assignments to any instructions. They will usually give you instructions on how you should give your answer, whether they want a decimal approximation or just a fraction. So this was an example where we needed to bring in some knowledge from outside. The problem didn't tell us what the perimeter of a rectangle was or what the formula for it was. That's something we had to bring from the outside. And that's usually what happens when you have word problems. Usually you're going to need to draw on some sort of information from outside the problem that the problem doesn't directly tell you. All right, let's look at an example of a finance problem. Where we can see how we use some of the ideas of linear equations to describe and represent things that go on with regards to money. So let's look at this problem. A person invests $15,000 total into an account paying 10% interest per year and an account paying 6% interest per year. How much do they invest in each one? If their annual interest payment is $1,260. So we want to make sure to read this, make sure we understand it. The person has $15,000 total that he split between two accounts. One of them pays 10% per year, one of them pays 6% per year, and the total amount that he gets back per year is given, $1,260. And we want to understand how much he has in each one of them. This isn't something that we can sketch out a picture of exactly, but we can use a table to understand some of what's going on. And so for this, we want to use the following fact. We're going to need to bring in this fact from finance that the problem doesn't directly tell us. We have that the interest earned in an account is equal to the principal in the account times the interest rate. So the interest earned in each account is equal to the principal in that account times the interest rate. Now we know the interest rates for both of the accounts involved, and what we don't know is the principal that's in each one. So we've got some unknowns here. So what we can do is we can set up a little table that gathers the information that we have for the two accounts that we have. So let's do something like this. Let's do the 10% account and the 6% account. And then we want the principal. We've got the rate, we've got the principal, and from these we can describe the interest. Now, we don't know how much is in either one of these. We do know what the total interest is, but we're going to need to express the interest for each account individually first before we can use the fact that the total interest payment is $1,260. So we don't know how much is in each one of these accounts. We need a variable. Now, at first glance, you might think we need two variables, one for the amount invested in the 10% account and one for the amount invested in the 6% account, but in fact, we can do a little bit better than that. We only need to use one variable here. What we can do is we can let A be the amount invested in the 10% account. So we can put that right here. So that how much is invested in the 6% account? Well, here we can use the fact that we know that the total amount of money that this person has invested is $15,000, which means that however much he's invested in the 10% account, the remainder has been invested in the 6% account. So in particular, if A dollars have been invested in the 10% account, I should have specified that this is in dollars. That means that 15,000 minus A dollars are in the 6% account. So if there's A dollars in the 10% account, that means that there are 15,000 minus A dollars in the 6% account. Well, now we can get expressions for the interest in each case. Now, the thing that we do have to remember here is that when we are using these formulas for calculating interest, we don't use the percentage, we use the decimal form of it. And the decimal form of 10% is 0.10, and the decimal form of 6% is 0.06. These are the ones that we have to use. Now, using those, the 10% account has an interest rate of 10%, a principal of A, we don't know that yet, but the interest earned per year in that account will be the product of those two. It will be 0.10A. And in the 6% account, we will be able to write down the interest earned there as 0.06, the interest rate, times the principal in that account, which is now 15,000 minus A. So now we don't know exactly how much interest is earned in either account, but we can express that interest earned in each account, and we know how much is earned total. So, since $1,260 is the total interest per year, we can write down that 0.10A plus 0.06 times 15,000 minus A is equal to 1,260. Because the total interest in the first account plus the interest in the second account has to equal the total interest between both of them. So now, again, we have a nice linear equation. It's got some decimals in it, which is something that we don't see all the time, but we do work with sometimes. So, simplifying this out, 0.10A plus, now 6% of 15,000, that's going to be 900 minus 0.06A equals 1260. Simplifying things down on the left further, we get 0.04A plus 900 is equal to 1,260. So at this point, we can continue solving this equation. Subtract 900 from both sides of the equation. When we subtract 900 from both sides, we get 0.04A is equal to 360. We'll divide both sides by 0.04 and get that A is equal to 360 divided by 0.04. This is the sort of thing that you'll want to plug into your calculator and get that A is equal to 9,000. So now we can say that based on this, A is equal to 9,000. We go back and check what A represents. A is the amount invested in the 10% account. So this tells us that $9,000 were invested in the 10% account. And, well, how much then was invested in the other account? Well, here we can go back and update our table. We now know that A was 9,000, which means that the amount invested in the other account is 15,000 minus A, so 15,000 minus 9,000, which would be 6,000. So we have our answer now. We have that $9,000 is invested in the 10% account and $6,000 is invested in the 6% account. Now, you do always want to double check when you get to your answer and make sure that this answer makes sense in the context of the problem. When you're working with real-world problems, usually the answers that you get won't be totally off the wall. And in particular, If you had gotten a negative number for A, indicating that this person had somehow invested a negative amount of money into the 10% account, well, that doesn't make any sense in the context of the problem, and so that usually means that something's gone wrong, that you have made a mistake, or occasionally, very occasionally, it means that the original problem was not well posed, meaning that it doesn't actually it doesn't have an answer. It doesn't make sense as posed. Usually, though, it indicates that a mistake was made somewhere. You should go back and check. We also want to check that this makes sense in terms of intuitive sense in terms of the problems, because there are some answers to this problem where even though they might technically be possible, wouldn't exactly match our intuition for what's going on, and that should make us suspicious. It doesn't necessarily mean there's a problem, but it should make us suspicious. For instance, in this problem, if we had worked out that A was just equal to 9 instead of 9,000, if we had worked out that A is 9, meaning that this person has $9 invested in the 10% account and $14,991 invested in the other account, that would be a little bit suspicious. That would be a little bit strange, odd for a real life situation to be in. And in particular, in that case, we would expect the total interest in that case to be very, very, very close to the 6% where nearly all of the money is invested in, and it's not. As I say, though, that's something that's a little bit more just a flag, just a yellow flag saying, hey, double check, make sure things make sense. You always want to do a little bit of a check to see whether your answers make sense. And if they don't, well, that might mean that there's a problem, and so you need to go back and check. Now, I should say that sometimes there are problems that just have solutions that aren't intuitive, and sometimes sometimes something looks a little weird. We go back and check, and everything checks out, and sometimes that's it. Sometimes things are just weird, but rely on your intuition. If something doesn't look right, if something looks like it doesn't make sense, go back and check, because usually that's because there's a problem and you can correct it.